I mean, we had an option to take where you say, like, I want to jump, give my... So we have that option.
Like, I had to go into the office first. So that's why I'm like,
You could have sent the PDF to us.
well,
Send us the PowerPoint.
yeah, so I was working on it yesterday, like, we had everything, and I left to you, I wrote it.
Yeah.
And then, I'm like, but it's, I mean, it's on the website.
Yeah.
So I'm so sorry to the
Yes, sorry, it was a very stressful night. Because I had to catch up with my mentor, I haven't seen in ages, and I had to announce my stuff. So you're right, in that kind of book, I'm reading nonsense.
No, I mean, I don't
You know, in the moment where this happened, I would have catch it up. It's like, just, you had some moment that I was...
No, it's fine because, I mean, I was with my colleagues, so they were getting lunch. So I went to the farmer's market in Imperial College just to go and
Because that was super useful.
yeah.
Okay, so we'll wait for like 1 minute.
Okay, I just had... Are you a doctor now?
I mean, I've seen like medical
doctor? No. I'm wondering what is the incubation period of chickenpox.
Oh man, why?
Because my child was with many other children on Sunday, and on Sunday they just told us, the mother of the child said, oh, my son has an early stage of chickenpox. We are going tomorrow to find my mother never had it, and she still survived.
Well,
She cannot get it now.
Ah, that's very dangerous.
Yeah, but the vaccine will not be effective for tomorrow. I'm going to see my mother tomorrow, so the vaccine will not get effective.
Well, maybe you feel like so you can learn the routine.
But she didn't find it, so I don't know how to do it.
Well, I don't know.
But do you think like I usually vaccine are the
So probably we'll start.
So I'm really gonna bring it.
so
I have no idea.
I just had this information right now.
Okay, good morning. So before we start, a couple of announcements. So as I said yesterday, like at the end of the morning session, we're going to take a photo of everyone in front of the UCL main building, which is just down the road, a very short walk that way. We'll all go together to that. So that's at 1:30. Next thing is there's pizza tonight, so you should come. Partly because of the photo and partly because of the pizza, we're ending lunch half an hour later today. So just check your timetables, but we're going to start the afternoon session half an hour later than normal. So those are the main announcements. First we have Maria Lomelli from Babylon Health, and so she's going to talk briefly about Babylon, and then we're going to continue with ABC with Sarah.
So thank you, Arthur, for the invitation. So I'm just here to give you a quick announcement about Babylon and what we do. So I'm a research scientist at Babylon Health, and I did my PhD at Gatsby, the Gatsby unit, and we have some collaborations with them, so it's very good to be here. So we are a digital healthcare company, and our mission is to we want to put accessible and affordable healthcare in the hands of every person on Earth. And basically, our company, we started 7 years ago, and at the beginning it was only a telemedicine company, but because of our mission, it's not possible to hire every single doctor on Earth, so we were trying to find smarter and more scalable solutions to how to solve this problem. So that's why we started with the AI and AI research teams. And so basically, we have 3 services, which is you can categorize them as the AI health services, the virtual health, and the physical health. So the typical user journey goes like this. So imagine you have your phone, either Android or Apple, and then you use our chatbot because you feel ill, and there's a series of questions that will make the user ask the user their symptoms and the risk factors, and then based on your answers, you'll get the next question and so on. And at the end, the main idea of the chatbot is to get triage recommendations. So basically, one of these outcomes can be that you need to talk to a doctor. So that's why we have the second part, which is the telemedicine, or you can have a video consultation with a doctor. And in some cases, the doctor might recommend a physical examination. And for now, in some countries, for example, in the UK, we have partnerships with the NHS, so you can go and have a physical examination in one of the clinics. And one of the services that we provide here is called GP at Hand, for people that are interested to use your NHS services with Babylon. And another thing I wanted to say in this slide is quickly that as I was talking to some of you at the industry day, and basically the chatbot on the back end has a natural language processing and large-scale graphical models inference engine, which is the thing that helps decide this AI about the next question and so on. But basically, because one of our missions is affordable healthcare, we've been in Rwanda since the beginning. There's an office there, and there's a partnership with the Rwandan government, and also the Bill and Melinda Gates Foundation has recognized the mission and has recognized our company there, in transforming how things work in the healthcare scenario there. And well, we are not only there in all the pink countries. It's the countries where Babylon is currently operating. We are delivering in the blue countries, where we are basically in the process of adapting our models for the local diseases and stuff. And then the orange countries is the countries that we're having conversations with, but we are not delivering there yet, so we're doing well. So some of the areas of interest. So I forgot to say that I'm in a research and development team called the Probabilistic Graphical Modeling team. And some of the areas of research, not only of my team, but also of the NLP team and of the cognition team, we have people that work in causal inference, so for example, the counterfactual diagnosis project or the data fusion project. And you might have seen the data fusion project at the poster session on Tuesday. We also work in amortized inference for medical Bayesian networks, some natural language processing models. So how do you, as I told you before, how do you find useful representations for the natural language that we get through the chatbot? And another thing is that if people want to know more about the natural language processing models, we have Francesco attending the school, so you can ask him more questions, because I got lots of questions about that. And finally, we also have some probabilistic programming for epidemiological models. And yeah, and the nice thing about being in the research team, for me, it's well, we do publish in some of the machine learning conferences. We have some publications already in ICML and iClear mainly. And well, we hope that to keep making the research team, make more contributions. And I think that all of the things that you've learned during the summer school will be very useful. So anyway, if you have any questions, please just don't hesitate to contact me. And thank you very much.
Okay, so I think now we will have the second half of ABC. Sarah.
So do you want to play with the light? Because there is present low, present high. Is that better? Better?
This one is low, I think, and the other one, this
Thank you. Now I need the computer to work. So what did you say that was a trick to make the computer? You turned that off and on?
This trick worked.
Yeah, looks like it is. Yes. Okay. Good morning. I hope you have a fresh mind now. You had a good night of sleep. So here is the summary of what we talked about yesterday. We talked about ABC, I hope you remember that, which stands for Approximate Bayesian Computation. So the idea of ABC is to perform parameter inference, and as we'll see a bit later today, model selection, when you have a complex model from which you can simulate data, but you cannot compute the likelihood. So the algorithm, the basic one, is nice because you can summarize it in a very small box in a slide. So I like that. So it's quite simple. You simulate from the prior, you sample from the prior, you simulate your model, and you accept or reject if the distance between the summary statistics of your observation is close to the summary statistics of your simulated data. And so yesterday we covered different points. One was what's the impact of the choice of the summary statistics? There is an ideal choice, but we cannot always find this ideal choice, so what do we do if we don't? We talked a bit about the post-processing, and I gave you some consistency results about where it does converge to, and that it does work the way we would expect it to work. So today I promised you two things. One is efficient algorithm for ABC, and the second is model selection. So hopefully the first one will take the first hour and the second one will take the second hour. Yeah?
One question. Did anyone try to see, so I understand that like most cases, like almost all the cases where we're going to use ABC is where we don't have a likelihood. But did anyone see like how much not having the likelihood is actually penalizing us? Meaning, so if I take a model where I actually have the likelihood, I use MCMC or whatever, I get an answer. And then I try to use ABC and I compare.
So that's kind of what I've done yesterday. Huh? In all the examples, I had in a way the likelihood. Sometimes it was very difficult to compute it, but I gave you the reference each time to illustrate. And to see that, in fact, in some cases we obtained very good results, even though we don't have the likelihood. Maybe better than, I didn't compare to MCMC, because MCMC, then it depends. It depends on your computational cost, it depends on your proposal. Again, it depends. It converges, but it converges. Also, the results is when the number of iterations tends to infinity. So I haven't. There might be comparison with MCMC. I don't know. But we'll talk about MCMC in a minute. So there are two types of algorithm mainly that are more efficient than the ABC basic algorithm that I talked about yesterday. One is based on MCMC. And the other one is based on sequential Monte-Carlo or importance sampling. So that's the two algorithms I would like to talk to you about today. Here are some references if you want to know more about these papers or these algorithms, but I will give you the idea with some equation and some schematic representation so that you have both depending on if you prefer equation or if you prefer schematic representation. So let's start with MCMC. You had a course in MCMC, so I don't have to remind many things, but that's the way I summarize MCMC to the students in general, often MSc students or undergraduate students. So that's the basic Metropolis-hasting algorithm. The idea is that you start from a parameter, you propose a new parameter using your proposal Q here, and then you accept or reject this parameter or this particle with some probability that is described here, which is the acceptance ratio, taking the minimum between 1 and this acceptance ratio. So you've seen that yesterday. You've seen many much more complicated version of MCMC, but that's the Metropolis-hasting algorithm, the first basic one. And the target
is the stationary distribution, which is here in our case the posterior, so it's proportional to the likelihoods times the prior. The advantage of MCMC is that we don't need to know the denominator, which is here the normalization constant, because it cancels out between the numerator and denominator. That's a basic of MCMC. Yes?
How do you do that derivation and stationary distribution?
You had a full course on MCMC yesterday. So I'm not going to touch all that. I imagine you had some, I don't know, was not there at the beginning of the is Michael here?
We talked about it.
You talked about it? Okay. Because I'm not going to cover all that. There are many criteria to do it. We can trust some, we cannot trust them. We can do a lot of figures. But I'm assuming now that you know about this. And so that's just a way to illustrate the algorithm. Again, we have some parameter, we perturbed it, we propose a new one, and we accept or reject. And after a while, after the burn-in period, when we assume we have found we are in the posterior and stationary regime, then all the samples are samples from the posterior distribution, and we can take all of them and look at the distribution they are creating. So that's MCMC. Great. So in MCMC, the main thing you have to compute is this term here, but unfortunately it involves the likelihood. Well, that's normal, it's a Markov chain Monte-Carlo algorithm, so there is a likelihood here, and in ABC we assume we don't know the likelihood. So how can we do an MCMC algorithm which does not require to compute the likelihood? So that's what Marjoram and Al worked on in 2003. And the idea they had is that now the target is not anymore the posterior distribution. The target is going to be this distribution, which is the joint between theta and z, so both the parameter and the simulated data, and of course with epsilon because we are in ABC, so we are not going, we will have a threshold epsilon. So that's just the idea. Instead of having the target being the posterior pi of theta given x, we'll have the target being pi of theta and z, the joint one, with epsilon given the data. So how does that work? This is the algorithm. So the algorithm is very similar than a normal MCMC. You start from a value, so you start from a realization of theta and z. So to have your first realization, you need to use the ABC algorithm just to accept 1z. So you start with that. Then for each iteration, you propose a new theta using your proposal, your kernel Markov kernel, like your Markov kernel. Then you simulate a new z. Then you generate a u and you accept and reject with this proposal here, with this acceptance ratio, here. I will show you why this is the correct acceptance ratio in the next slide. And also we accept if the distance between the summary statistics and the observed data, taking into account the summary statistics, is smaller than epsilon. So this is as before, but in addition we have this step. With the accept and reject. And then, if it's fine, we accept it. If it's not, we keep the previous one exactly as an MCMC. Yes?
So we use the prior. We use the prior for acceptance now, but are we not using the prior to generate thetas anymore? Or is it...
Exactly as in the MCMC.
Right, so we're not, I mean, like before in ABC, we were using like a prior.
Yeah, no, exactly. So we are in an MCMC scheme. So we use the prior only, but the first one is drawn from the prior. The first initial one, but then we use the prior in the acceptance ratio only. Yes?
Can you explain why you generate U randomly? Why do you generate that randomly?
We want to accept with probability a minimum between these two things. So we want to accept with probability P being defined here. And to do that, one way is just to do this step. One way is just to sample from a uniform and take it, accept when it's smaller than P and reject when it's larger. So it's just doing this step.
Does that now correspond? I don't understand why. I just don't understand why this isn't deterministic. We're accepting samples based on a bound that we set in advance, rather than accepting them or rejecting them at random.
So we accept and reject exactly this way, but this algorithm can be written as it is here, or it can be written as we sample U from a uniform between 0 and 1, and we accept it when U is smaller than P, and we reject it when U is larger than P. This is exactly equivalent. That's the way we implement it. And that's the way I write it here. Okay? Yes?
Sorry, I'm probably misunderstanding something or missing something. Don't you just keep strictly less samples than before this way? Because you still need your epsilon condition, but you also now have the U condition.
Now, basically, instead of sampling from the prior and simulating, accepting, rejecting, we are constructing a Markov chain. So it's a different way of thinking. We are constructing a Markov chain in the space of parameter, and the stationary distribution of the Markov chain will be the posterior of this joint. Okay? So why does that work? Why do we have this ratio with no likelihood? It's kind of magic the first time. So why does that work? The idea is not that difficult if you write everything down. So the target distribution, I said just at the beginning, is this thing. So it's the joint between theta and z, given your data and given epsilon. So the target distribution is sampling from the prior, simulating from the model, and accepting, rejecting if we are inside our region that we accept, so epsilon away from the real data. And the kernel, so the Markov kernel from our MCMC is this one. So we propose a new theta, given the previous theta, and then we simulate z given the theta. So here I just summarized the algorithm before. And the acceptance ratio is always the target divided by the target from the previous particle, multiplied by the proposal, and divided by the proposal from on the other way. That's just MCMC. So here we have the target from the new parameter, the target for the old parameter, the proposal going from the old parameter to the new to the old, and the proposal from the old to the new. So if we write that down and we replace pi epsilon theta z and pi epsilon theta t minus 1 z t minus 1 by the value here, we just see that the green terms cancel out, the blue term cancels out, so all the likelihood terms cancel out. And we obtain this thing that does not depend on the likelihood. So the only idea and the only trick to make it not depend on the likelihood is that we change the target to be from the posterior distribution to the joint between theta and z. That's the trick. And that's going to be the trick for many things today. That if we don't want to have the likelihood involved in our computation, we need to focus not on the posterior distribution, but on the joint between theta and z. And then we can integrate out z after, but the distribution of interest is that one. Do you have any question here? Yes?
So compared to yesterday, is this just strictly like better for what we want to do? Like we were just like sampling from the prior, it seemed like it was naive, like to reject the epsilon. This just seems like a bit more like principle in how we're generating the thetas. Is there like, is this just kind of the next step? Like is it what people are kind of using now, or can you use advantages of the previous approach that like are not captured by this?
It depends on people. In practice, I've used a lot the algorithm that I'm going to present next, which is a sequential ABC, which can work very well, but we have far less guarantees. So the one we have guarantee of, like all the consistency algorithm, etc., are the one I presented yesterday. So if you want to really have proof that it's going to be consistent, it's going to follow all the things you want it to follow, the proof is from the algorithm from yesterday. But this is an MCMC, so all the proof that works for MCMC will prove that under all the conditions of MCMC, we will converge to this pi theta, this target distribution. It will not then say that this target distribution converges to, there is not proof of if it's going to be a normal distribution, all that it has not been proven. And for the next one, it's even more complicated. So then there is, if you want a proof or if you have a computational constraint and you want to obtain something as fast as possible and you don't mind if it's a bit off regarding the proof. That's always a threshold. Other question, yeah?
I still don't understand this slide before I'm reading. So essentially, your acceptance or rejection based on the U condition is...
This one?
Yes, so you'll generate...
So, okay, I will rewrite it differently. Do you prefer?
It's not that I don't appreciate this equivalence to P.
Okay.
It's not that. It's that why is this stochastic fork? So in
Yeah.
We accepted it if it gave us the right distribution.
Yes.
So the stochasticity is about exploration there, and then we kind of make a projection or make a selection to make sure it's giving us in the area that we want. Now here, you generate stochastically your theta, generate stochastically your z, which should explore your space enough, and then we have this selection thing that's deterministic based on t and epsilon.
So this is this part that worries you, not that part.
No. It's the fact that I don't understand why.
Misunderstanding about statements.
Am I misunderstanding?
You accept deterministically if the density is higher. If the density is lower, you accept the probability. There's always value there. So if the density is higher, that ratio is always greater than 1, and that's why no matter what u is, you always accept it. This is entirely consistent with what we have at
I misunderstood yesterday. Thank you.
Okay, cool. Because here I assume that MCMC is a done deal. Other question on this one? Okay. Oh yeah, sorry.
Can you say that we are indirectly estimating the likelihood here?
We are not estimating.
Cancels out, but
We're not estimating likelihood. We are still estimating the posterior distribution that involves the likelihood.
yeah. But
We are not estimating the likelihood, but we have a model. So from the beginning, we want to infer the. We are Bayesian, so in Bayesian we always have the likelihood somewhere. We just don't. We cannot compute it. So the second approach is based on sequential ABC, and I've worked a lot on this, so I'm going to talk to you about my work on it. But many other people worked on it before me. So the idea is that instead of fitting one epsilon that we want to aim, we are going to do many epsilon. First, we will do an epsilon that is very easy to reach, so with the basic ABC algorithm. And then we'll do, what if we push an epsilon a bit smaller? Can we go there from where we were before? And then what if we have an epsilon a bit smaller? So we'll do a sequence of epsilon so that it's computationally less expensive. So first we'll have a very easy target, and then we'll decrease epsilon step by step to go towards the posterior distribution. That's the idea. So basically we'll have many population that is called. Population is for different value of epsilon. So we'll start with an epsilon 1, which is very easy, and we'll have the posterior for this distribution, epsilon 1. And then from that posterior, we'll go to another posterior with epsilon 2, which is a bit smaller than epsilon 1, etc. I think I have an illustration. Yes, I have an illustration. So we start with sampling from the prior and accepting and rejecting exactly as before, as yesterday, with an epsilon that is super easy. So an epsilon that is large, and we will accept not every particle, because otherwise it's not much, but a lot of particles. So that's not computationally too expensive. Then we'll keep this population, so this sample that we have. And what we will do is that we'll perturb them a bit, do some Markov chain. So we'll sample from them with some weights, perturb them a bit, and compute again the distance between the summary statistic related to this data and the summary statistic of the observed data, and put a threshold on epsilon that is a bit smaller, epsilon 2, that is a bit smaller than epsilon 1. And we'll do that sequentially for many values of epsilon. Do you have questions on the basic ideas of the algorithm? No? So let's go towards not the basic idea, but how it works in reality, in practice. So this algorithm comes from a population Monte-Carlo algorithm proposed by Capet and others in 2004. So population Monte-Carlo is, as MCMC, it's when you have likelihood. But it's from that the ABC-SMC idea came from. So the idea of population Monte-Carlo is the same as to have different population. Here they don't have different epsilon. But they have different population and they have importance sampling. Who knows about importance sampling? Just to have an idea. Okay, most but not all. Did you hear about importance sampling here?
Yes.
Okay, so most of you should know. Thank you for confirming. So this is based on importance sampling. So the idea is that now T is the population. So we'll have different population, T equal 1 to T equal capital T. And for each population, we'll have n particles from 1 to n. So at population T, we have a sample theta 1t to theta nt. So given that you have a population like that, to go to the next population, you will sample from using a perturbation kernel, Q, and then you will associate weight to each of your sample. And the weight is proportional to the prior. No, sorry, P is not the prior here. P is the target. The target divided by your kernel. So, okay? So the way it works is that all your parameter has been sampled independently from a kernel Q, or distribution or proposal Q, and they will be associated to some weight, and the weight is the target divided by the proposal. So in general, the target is a posterior distribution, and it involves the likelihood. It could be anything else, huh? But P is your target distribution. So at the end, what you have is that each of these samples here, you have the sample and the weight, and the sample and the weight together form are a sample from the target distribution. Any question on population Monte-Carlo? Yes?
Do we know the target distribution?
So that's assuming that you know a target distribution. That's for any target distribution. So as MCMC, you have a target distribution in mind. Usually in Bayesian computation, it's your posterior. Of course, on ABC, that will be tricky because it involves the likelihood. I just wanted to give you the population Monte-Carlo in general first. Yes?
What do you say, like, why population Monte-Carlo versus non-population? Like, what is the advantage of population Monte-Carlo?
In general?
Yeah.
Okay, can I call a friend? I'm going to call Olivier Capet. Now, it's combining both the idea of MCMC, because Q will be a Markov kernel, and important sampling. I'm pretty sure they proved in Capet and al. some better convergence rate, etc. But I haven't looked at the details of them. I should. Huh? Olivier Capet is one of my PhD supervisors, so I should have asked him. So in ABC, we can use a population Monte-Carlo algorithm, but we need one that does not involve the likelihood computation. So in general, the target is the posterior that involves the likelihood computation. So we'll do the same trick as in MCMC to avoid the calculation of the likelihood. We'll take into account this joint target. So that's exactly the same as before. And the joint target is the joint between theta and z that is here. And we'll have the same trick that makes everything cancel out. So the idea is to produce at each population, or that I call iteration or population, depending, the sequential ABC algorithm will produce a weighted sample. So now we have sample, but we also have weight, and they are going to be sampled from the target distribution. Again, I have a slide on why does it work. Oh no, I just first explain how it works. And then why does it work. So how does it work, and why? How do we do it in practice? So for each population T, we have the particles from the before. So I come back from first step. First step, we sample from the prior, and we have a very easy epsilon, and we accept reject with this epsilon as yesterday. So that's population 1. Then we go to population T equal 2. What do? We are going to sample theta from the previous population with the weight. Now every particle has not only a value, but it has a weight associated to it. So we are going to sample from the previous population with some weights. Then we are going to perturb this new theta with some Markov kernel K. That's the second step. Third step, we are going to simulate data from the model using this parameter theta tilde here called. And fourth step, we are going to compare this simulated data to the true data using the summary statistics and accept or reject with our new value of epsilon. And that's the ABC-SMC algorithm. So the proposal distribution, in a way, if you want to write it mathematically, to propose a new value of theta and z together, you sample from the previous population, so J is an index over all the parameters from the previous population. You sample with some weight omega, and then you perturb with your kernel K, and then you simulate Z with the parameter, and then you accept reject. Yes?
Where do the new weights come from at time t?
Oh no, I haven't computed here. Next slide. So the weight is exactly as in population Monte-Carlo. It will be a ratio between the target and the proposal. And I will show next slide how to compute them. I thought it was previous, but it's next. Yes?
So you call the proposal distribution a kernel as well, right?
Yes, sorry. I don't know how it was called yesterday in the MC-MCMC HMC course. So the proposal distribution MCMC is usually called a Markov kernel.
But it's a distribution.
Yes.
And this
It's a conditional distribution.
kernel, it's a different thing.
Sorry?
And the perturbation?
That's the same thing. So, sorry, that's a lot of vocabulary. Everybody, and the word kernel is used in many fields for the different things. That's really, I don't know, people love the word kernel. I think it's used for many different things. So in MCMC, Markov kernel or perturbation kernel is the distribution that is used to sample new parameters given the previous parameter. So it's called sometimes perturbation, sometimes transition, sometimes proposal.
But if you use the perturbation to get the proposal.
So here, basically here I do a combination of many things because, so that's my proposal, my total proposal, but I do many steps for this proposal. And most of the people only have one step, they just have something like that. Here, I sample from the previous population with some weight, I do that, plus I simulate, plus I accept, reject. So the summary of all these steps is here. But some people will call that itself a Markov kernel. So we could call that a Markov, it's really a question of vocabulary in the field. Yes?
Sorry, maybe it's clear from notation. I'm confused. So what we finally accept as the new parameter, is that perturbed data, or is that the...
It's not the data that are perturbed, huh? It's the parameter.
Sorry, is it the perturbed parameter that we're accepting later, or the one we sampled?
No, it's a perturbed. The notation I hope they are correct, yeah. It's a theta tilde that we take.
I see. We always...
And we simulate from the theta tilde.
Gotcha.
I haven't done the typo here. Yes?
Notice that there is a subscription as a thread of T in on the perturbation kernel K. So it's K depends on T.
So K can be many things, and I will talk about it. I have 5 or 6 slides on that in a few minutes. So let's go to the weight, because I thought I did this slide before, but that's the opposite. So how do we compute the weight? The weight is exactly as before. It's the target divided by the proposal. So I just recalled on the top what is our proposal, because it's a long equation, and I didn't think that you will just remember from the previous slide. So I copied it here. So the proposal is on the top, and we have the target divided by the proposal. The target is the same thing as ever. Like so far we've done same target for many slides. And the proposal is here. And you can see that, I haven't done many steps, but we can see that these terms cancel out with that term, because this term and that term does not depend on j, it only depends on I. So this can go outside of the sum, and it will cancel out with that term. So the likelihood, again, will cancel out. And we will obtain a term that does not depend at all on the likelihood. So it's the same trick as in the MCMC. That is because we target the joint distribution and not only the posterior. Does that answer your question on the weight? You're welcome. So that's the summary of the algorithm. And again, it's more complicated and it's more technical, but once you have the algorithm, it's not that difficult to implement. It's like it's kind of a mixture of ABC and MCMC with some accept reject. So the idea is you first sample from the prior, you generate data, you accept reject as before for the first population. And once you have your first population, you will then sample from the previous population with the weight, perturb the parameter that you obtained, because you don't want to always stay exactly at the same place, you want to move a bit, perturb with some kernel, sample the data, new data from your simulator, and then accept, reject if it's smaller or not from the epsilon. And compute a new weight for all the particles that you've accepted. Maybe I'll ask you to implement it later today. Any question here? Yes? So that I'm not sure I'm consistent everywhere. Here, capital N is, so T is the number of population, and I have not have, so T is the population, and I don't have the last one, it's capital T, but I don't have. Capital N is the number of particles in each population. I might have called it some small n in some other slide. That's not impossible.
So the initial width, shouldn't that be 1 over T?
No, 1 over n. So in each population T, we have n particles. Yes?
I'm wondering where are you decreasing the epsilon?
So epsilon here is epsilon T, and it will be a sequence of decreasing value. I don't tell you how I do it. It's just different value. That's another slide. I'm not doing everything in the same slide. You want everything in the same slide? Okay. This is everything in the same slide. So the two things I've worked on, like nearly a bit of a while ago, is working on the perturbation kernel and the threshold schedule. Because of course they will play a role. Huh? Of course, your kernel plays a role exactly as in any Monte-Carlo based, Markov chain Monte-Carlo or population Monte-Carlo based algorithm. The kernel plays a role, and if you find a bad kernel, you will have a bad convergence. And the same way epsilon T plays a big role. You had a question, yeah?
Is there a variation of this algorithm where you introduce resampling to stop the weight distribution?
So here there is a resampling in the step 7. We sample from the previous population.
But sometimes if you run this algorithm for long enough and you have a threshold schedule that's quite long,
Yeah.
you end up having paths that are quite dependent. So then do you not experience problems where you're importing weight distribution?
No. But it depends on your kernel again. So if your kernel is a Dirac on the previous particle, yes, we'll have dependence. But if your kernel perturbs well enough, we don't have that. Again, no, it depends. I should be honest. It depends on your kernel, of course. If you take a kernel that moves in a very, just slightly and not enough, you don't explore enough. And exactly as any Markov chain Monte-Carlo also, if you have a very small kernel, you will never move and will never explore. So in the next few slides, like, where is time? Yeah.
How do you deal in the case that you have something like degeneracy, where one particle in the population is dominating all?
So here it's not a big a problem because we sample in step 7. We sample from the previous population. So if one has a very low weight, we will not sample from it. So we don't suffer from the weight degeneracy, fortunately enough. Because weight degeneracy is mainly when you keep all the weights, all the particles. Here we resample from the previous. So if someone has a small weight, we just will not pick it. Yes?
So your weights are proportional to your prior, which means that if your choice of prior is bad, you will continue to be weighing according to that, right? Why aren't your weights proportional at all to the distance?
So the weight is what makes you sure that you will converge to the posterior distribution. The posterior distribution depends on the prior. So we always need to remember, we are in Bayesian setting. The posterior distribution is proportional to the prior times the likelihood. If the prior is bad, your posterior will be bad. But in a way, we don't want to deal with that here. We want to target the posterior, whatever bad it is. Okay? So I just proved in the previous slide that we are targeting the posterior. And this algorithm doesn't influence, in this algorithm, the prior doesn't influence the posterior more than any other algorithm. But again, if the prior is bad, you'll have a posterior that is far away from your maximum likelihood, as in any. Okay, so you're ready to go to the kernel? We'll go to the kernel. So the idea is that we could use many kernels, but we want to have an adaptive one. We want one that takes into account where we are. And I think I will need to draw something here because It's much easier to explain with, should I draw? Yeah, here, I'm going to draw here. Imagine we are in 2 dimensions. Can you see with the light? Yeah? And our previous population is like that. That's fine. It's very linear, but that's just easy to explain. Okay, that's our previous population. Now the idea of the algorithm that we are going to pick a particle from this previous population with some weights. We are going to perturb them slightly and then simulate from the new parameter and accept reject with a different epsilon. We have different choice. If we have a perturbation kernel that is like that, it will give us some result. We could have a perturbation kernel that is like this, that takes into account the side. But there is always a trade-off in a kernel. If we have a kernel that is too local, so that just perturbs a bit, we'll never move the particle, basically. We'll have the problem you just explained, that we will have a very high acceptance rate, because we'll barely perturb, that's fine, but we'll not explode the space enough. If we have, on the opposite, a kernel that is very spread and that perturbs a lot, we'll explode, that's for sure, but we might never accept a particle, because if we are here and we use a very, very broad kernel, we might propose something that is there and we'll always reject. So there is this trade-off, exploration, exploitation. I'm sure you've heard that in other course, between exploring the parameter space and ensuring that we have a high acceptance rate. So a lot of people thought about it. I was not the first one. I may be the first one doing it in a, let's say, in a general way for ABC-SMC. So what's the idea of finding the best optimal kernel? The idea is that we want a high acceptance rate, okay? So that's the second point. It's the easiest to explain. So we want to be able to have computational efficiency. That's the point of ABC-SMC, so we don't want to lose that. But we also want to make sure that we are going to perturb enough so that we are going to represent well our population. So basically what we want to say is that pi theta t is the posterior, that's not me. Pi theta t is the posterior for population epsilon t. We want that all the procedure I just explained, so sampling from the weight, sampling from the previous population with the weight, and perturbing and simulating will give you a good approximation of this pi epsilon t. We will re-rate them, so we are sure that we will obtain a good one, but as an important sampling, we want our proposal to be as close as possible to our target to avoid having very bad degenerated weight. And there's also some theoretical requirement that we want for convergence, but that's far less important than the 2 first points. Any question here? No? So either it's super clear or it's not clear at all. So what I want to guarantee is that the kernel is such, the perturbation kernel is such that we perturb well enough, but not too much. And how do we say, and how do we measure that we perturb well enough, but not too much? We look at how do we perturb, and what's the population we create when we've used this perturbation, compared to where we would like to end up. And we want these two things to be close enough. That's what the first point says. The second point says we want to be computationally efficient. So that's the two things we want to be close to each other. Let's start by the first one. The first one is what the algorithm does. The algorithm, what does it do? We had the previous population. So theta t minus 1 is sampled from the previous population. It will be perturbed, and then it will be, we will simulate from this perturbed parameter using the model, and we'll accept reject according to some epsilon. And we integrate our dz because here we only focus on the theta. Divided by some denominator that's proportional. I'm not going to give you the proof, but the denominator is exactly the acceptance rate. That took us some time to find out and to derive, so I'm going to spare you that. But alpha, which is the denominator, is exactly the acceptance rate. And we want that to be similar, or as close as possible, to sample from the previous population and sample from the new population. Imagine you had the new population. If you are sampling from both of them independently, you want these two algorithms to give you the same thing. So we want the distance between these two quantities to be as small as possible. So as many people, and you've seen that I think many times the last week and a half, to evaluate the distance between these two distributions, we use a KL divergence. And here there are a lot of math that I just don't write here. The main idea is that the KL divergence can be written in the sum of some terms. One is computationally tractable for some value. This is an ugly term. Just tell you that this is a term that exists. And the other one is the acceptance rate log alpha. So in summary, we want to minimize the KL divergence between these two distributions. There are three terms here. The last term does not depend on the kernel, so we don't care about it, because what we want is to choose the best kernel. The first term is a term that can be computed sometime. The second term is the acceptance rate. We want to minimize the KL divergence, but we also want to maximize the acceptance rate. That's the two things we want to do. So in fact, to do that, to minimize the acceptance rate and maximize the acceptance rate and minimize the KL divergence, I knew that I was saying something wrong. We just can maximize the term that remains, which is this term here. If we maximize this term, we will minimize that one and we will maximize that one. That's it. That's the only idea of our paper. So we have this term, and we want to maximize it. Find a kernel that maximizes this thing. Okay, this is ugly. Huh? It doesn't involve the likelihood. We are safe. But that's not a very nice term. The nice thing is that this can be computed for some specific family of kernels. And here we focused on normal or Gaussian random walks. So for Gaussian random walk, we can compute these integrals analytically. So for Gaussian random walk, I can, if you tell me I want a kernel that is a Gaussian, so you have the previous parameter and you perturb it according to a Gaussian, I can tell you what's the optimal covariance of your Gaussian random walk. Do you all know about Gaussian random walk? Yes? No? We just have the new parameter theta t minus 1 is sampled from a normal distribution centered from the former parameter with some variance. And here, maximizing the term that I had in the previous slide will tell you what variance to use. As I said, there is like a trade-off. Using a small variance will do just a small perturbation kernel and will not be very efficient. That will give a high acceptance rate but not explore enough. High variance will give a small acceptance rate but will explore enough. Here, using the equation from the previous slide, you can find the optimal sigma. Then we did other small ideas is that we could go even further. Maybe we don't want to use the same sigma here for every particle. Maybe here, so if I draw again my previous sample, maybe when I'm here, I want just to have a sigma that looks like that. And maybe when I'm here, I want something more like that. Why would I have the same sigma for the whole population? So we proposed some optimal variances, and that's the last equation. Don't need to know about it, just minimizing the KL divergence, minimizing KL divergence as in the previous slide, assuming now that we have a different variance for all the particles, can be written explicitly, and there is a method just to do that. So we propose different kernels. One where we have the same kernel with the same variance for the whole population, and one where we have different kernels for different part of the population. Any question here? Yes?
So is there about an equal amount of theoretical work on this also this threshold update rule, or is most of it seems like there's maybe with these kernels there's more you could actually do than with the update rule, or it's more.
So I go to the threshold just after.
Okay.
Yes?
So this relates to evolution strategies.
Two?
Evolution strategies and evolutionary algorithms.
I don't know.
Similar to particle theory.
Yeah. We can think about it together. I think there are some links because people. Yeah. Yeah. I see the link, but I cannot give you a formal answer. Yes?
Can you go back to the KL term?
This one?
So this is the term basically when we minimize it, we get we increase the exploration.
So if you maximize that term, you will find the optimal parameters. So if KT has some parameters, so here we assume that KT is a normal distribution with sigma t, the covariance matrix being our unknown. If you maximize this with respect to sigma t, then you find the optimal sigma t. And since KT will be normal in that case, we can analytically solve this integral and just write down the link.
Simplistically, you would maximize acceptance rate.
So doing that, it's a trade-off between maximizing. So maximizing that will mean maximizing the minus scale divergence plus log of acceptance rate. So it will do directly the trade-off between minimizing the K and maximizing acceptance rate. So that's the nice thing here. We are doing both at the same time. By maximizing that, we are both minimizing the K divergence and maximizing the acceptance rate.
So basically, you want the Q and the Q star to be more different.
We want Q and Q star to be as close as possible. So we want to minimize the difference, but we want to maximize the acceptance rate.
Is this then related to exploration? Or?
Yeah, it's how would I do the exploration? It's related to exploration in the sense that Q star is really the one you want, and Q is the one you have using the procedure. And if Q were perturbing too locally, then you will not recover what you want. So that's related to exploration. Any other question? Hmm?
Is the covariance matrix always guaranteed to be positive definite in this case?
Yeah. Yeah, it's a we are, yeah. So here are some results on real data, not real data, simulated data, but real models from biology. Don't need to understand all the models, but here are two models that are interactions between proteins and genes in a biological system. The simulator is based mainly on stochastic differential equation. So it's very difficult to write a likelihood in that case. Very, very difficult, or you need to make assumptions on the system. And here I compare the running time and the number of simulation using different perturbation kernels. So one is a uniform perturbation kernel. So you use a uniform random walk centered on your previous particle. One is a normal, what I call normal component is normal component-wise. So for each of your parameter, you use a normal distribution. You don't do the multivariate. You do the one with a diagonal covariance. Then and then there are many multivariate one based on the whole population, but all the multivariate ones are the one based using my approach, basically, the one where we maximize the Q term. And we can see that maximizing your Q term, you always have a smaller running time and a smaller number of simulation. That makes sense. That's exactly what we maximized. Huh? So it does what we want it to. And the OLCM is the optimal local covariance matrix. So that's the one where we use a different covariance matrix for each particle. I don't want to explain the FIM that are not so interesting, but the main message here is that the multivariate approaches using, when we optimize the kernel, does work pretty well. Again, that's not a surprise, that's exactly what we maximize for. So it's not magic. Here is just some computational cost. So just in ABC in general, the computational cost is usually simulating your, from your model. In most of ABC, the problem is simulating your model. So if you increase the acceptance rate, that's the best way to have a better computation, a lower computational cost. Because less you have to use your simulator, better it is. But still, we had for this paper to compare the computational cost of computing this kernel, because I have to maximize all these things. What if it's, you know, what if we find the best kernel ever, but in fact, it takes us forever to do that. So here we just showed that computationally doing this multivariate with optimal local covariance metric is not that expensive at all. And it's certainly not expensive compared to simulating the model. Yes?
Is this, like you were talking yesterday about like multimodal models and
yeah.
whether or not like, you know, we can actually find multiple modes with MCMC. Is this the same for these kind of methods where you have a proposal or like a perturbation kernel?
So population Monte-Carlo are much better in general than MCMC algorithm to identify multimodal because they are based on a population. As long as there are enough particles for each population. Because if there are enough, when you sample from the prior, imagine there were two modes far away. When you sample from the prior, you hope that some particles will end up in the first mode, some in the second mode. Since you don't have only one particle that has to move, you have many particles. So from the if from the first population you grab these two modes, then you will continue to stay there.
So it depends a lot on the initialization, like just like how well we do in the first couple steps then? Or, like,
yeah, it does. But as long as your perturbation kernel could maybe help you to jump from one mode to another. But that's like in MCMC, we don't really have guarantee that it does it. So I will more say that if n, the number of particles inside the population, tends to infinity, we'll grab it. It never tends to infinity, we are in practice. So if you think that there might be multi-modes, I would suggest to not have many thresholds. Now, T is not that important, but a large population is very important. That's what I do in practice for my problems when I suspect that there might be multimodes. So, to answer the second question, yes, epsilon plays a role. It plays a huge role. And even though there are some solutions, they are not an ideal solution. So in a way, that's maybe the reason why not to use ABC-SMC. I don't know if I should say that, but yes, I do say that. You need to be very careful with your choice of epsilon threshold. Basically, ideally, the final value should be as close as possible to 0. The first one should be easy. That's fine. And you want to minimize the number of simulations. That's the aim of this game. So you want to minimize the number of population, because the number of population plays a role on the number of simulation. And you want to maximize the acceptance rate per population. And there is not a magic trick for that. So I think in the next slide I have two, yeah. Most of the people who make it work very well in biology use trial and error. That might sound strange, but that does work well. So if at some point the population is completely stuck, they're like, oh my God, maybe something has been wrong. Maybe we should not have decreased epsilon that fast. Let's go back. So if you implement ABC-SMC on real data, please have some checkpoints where you save your populations. That's a good practice in general, because ABC-SMC, well, now we have better computational resources. When I ran ABC-MCMC 6 years ago, yeah, my code was running for a few weeks. So first you want checkpoints if computer crash, but also if you realize that your threshold is not good enough and you want to go back to the previous population, you want to make sure you can do that. There are computational resources for that, and there are packages that implement that all in a nice way. You don't have to implement it from scratch. Then there are some adaptive approaches, people who suggested different ways of finding the best epsilon threshold. Most of them are based on quantile, exactly as for the ABC approach. And mainly my main message is that doesn't work, or that cannot work. So here is a very simple example of when it doesn't work. It's an example I made up. Huh? It's rare to have an example like that from real data. So what do you see here? Theta on the x-axis. On the y-axis, the distance between, or G is the summary statistic here, sorry. G is the summary statistic on the model. So here we have a deterministic model, but I just wanted to show that there were a problem with the approach. So we have the y-axis is the distance between simulated data coming from parameter theta and simulated data coming from the real parameter theta star. And the dots are your population. So imagine we first start with a distance around 150. Is it 150? Yes, 150. You sample from the prior, you accept, reject all the ones with, that are larger than 150, and you obtain all these dots here. Great. Then second step, you take the quantile, maybe quantile 0.1% of the distance between the simulated data and the real data. You have a new threshold that is 90. Okay? You run your ABC-SMC, and the second threshold will be 90. The problem if you do that is that you will arrive here. And if you continue to do that, you will end up in this local optimal, but you will never go to this global optimal. So depending on the choice of alpha, which is the choice of the quantile threshold you use, you might never end up in the real part. And what I show on the right is the percentage of failure. So I run this algorithm many times, and failure means that we end up in a local optimal, not on the global optimal. So if alpha, the quantile, is large enough, you will manage to, if alpha is small enough, you will manage to have a very small failure threshold, and you will manage to converge to this local optimal. But if alpha is very small, it's nearly as if you don't do sequential ABC, because in fact it's going from a large epsilon to a very small epsilon. Then it's not doing a sequential ABC. So basically this slide is just to show you that there might be, it might not work. In reality, it's very rare to have a likelihood function that looks like that. Huh? But it might happen. Who knows? Yes?
So for the trial and error approach and like just seeing like which ones will work and which ones won't, what is the evaluation at the end that tells you like how good of a job you did? Is it just like how, like if you think you can make your distance smaller, or is there like some intuition about your distance that you have to have?
But this is a very good example. So imagine here, from here, you did have some point that falls in this area because you had n big enough. So your smallest distance, imagine, was around 10. And then at the second population, your smallest distance is never smaller than 50. Is it 50? Yeah. Never. And the third population, neither. And the fourth population, for the one population, you say, oh, that's just by chance. So at the first population, you had a distance that is very small, around 10. But then in all the other population, you never go any distance smaller than 50. You can think, oh, maybe I did something wrong here. Maybe I'm going in the wrong area.
Right, so for all of your populations around 40, how do you know that there might exist something better than
You might not know.
Is it just intuition like about the problem and like how big, how small the distance is?
If you knew the likelihood, you will know, but you don't know the likelihood. That's a problem. So no, especially because if you work in high dimension, there is no way to know, unfortunately.
For trial and error, like what gives you steps to really understand, like you run this algorithm a lot, you have a lot of intuition about like your distance metric that you have and like how low you can go or something, like you know a lot of the summary statistics, like what usually tells you like if it converges, like or, I guess, I don't know, it seems difficult to do trial and error if you don't really understand how well.
Yeah, I would, the way I would do is always recall the distance, the smallest distance you obtained. And if that happened only on the first population, not anymore after, I would say there is probably something wrong. Also, what a lot of people do is that they also plot the predictive, posterior predictive at each population. If the posterior predictive is quite good at for the beginning and then it starts getting bad, you're like, oh, I went in the wrong direction. Because often it's difficult to plot your parameter space, because if you're in high dimension, you cannot plot anything. I suggest that we do a few minutes break. We don't have time to go out. That's what I've heard, because if you all go out, there is no time. But we can like... I'm not going to show the 2 next slide, about the 3 next slide, because that's a technique that is not that important for you to know, and I prefer talking about model selection. So let's have 2 minutes of breathing space. You're not allowed to go out, huh?
I work on similar methods.
Okay.
That's of course with likelihood, not so it's a little bit different for me. But if you're doing resampling, right? And so this theta bar, this is the resample particle
so I need
to
to
the next
remember.
time instant, right? After you perturb it.
Yeah.
So if these are very close, and the weights, let's say one of the weights is 1, and all the other ones are 0. Isn't it possible that this is just
that would be very bad. Yeah.
Rank 1, so
hopefully, when you do the sequential,
right. So
it doesn't happen because.
I would assume in the beginning all of them have very similar weight because the threshold is very high.
At the beginning, it's 1 over n.
I see.
So it's uniform. And then, especially if you use this local optimal, you're exactly. Basically, it's an important sampling. So you're optimizing the proposal so that your weight. I don't say it this way, but
I understand.
So you're maximizing your proposal so that your weights are, in a way.
And is there a connection between, so what we're doing in this algorithm here is we have an epsilon t for each time instant. So kind of like, it's kind of the same thing as in particle filtering, where at each time instant you would expect that you're getting more data so that you'll be going closer to the true parameter value. Is there a connection between this and tempering? So in one case, like say in the first time instant, you're very relaxed, right, with the summary statistic.
So the sequential Monte-Carlo algorithm, SMC sampler.
Right.
So that's why this algorithm has tables. It's called ABC-SMC and ABC population Monte-Carlo. As you've seen, that it's always 2 city excitation. We both propose the algorithm same year.
Yeah, it's weird.
2 different names. But the sequential Monte-Carlo algorithm from Del Moral et al., which is not in an ABC setting, is exactly that. It's using a temporal. And I'm implementing that for you. So you don't have that, but you have a temporal.
Yeah, it's interesting because I think there's a connection between the two.
There is a real connection. And you can even prove that there are. Del Moral also wrote a paper on ABC-SMC proving the connection and doing some. So there is a definite connection.
Thank you very much.
You're welcome.
So basically, the whole point of ABC is to try and invert the model to function, right? To try and find the input to the output. So why is it?
In every Bayesian inference.
Sure. Okay. So why is it that ABC, regardless of all this extra stuff that's on the top of it, right? The basic idea is let's just guess something and see if it fits. Why is it guessing? Why isn't it like stochastic gradient descent if we've got gradients available, or just sort of neighborhood search? You don't. Genetic algorithms.
Because we want the word posterior. We just don't want one estimate.
Because this is the thing, like
if you wanted one estimate, so what would be the gradient? Because we don't have the gradient.
Well, it's the thing, if you do have a gradient, you use your function analytic, sure. But even if you don't, right? You pick a theta, it has some epsilon. Oh no, that's not quite right. Well, okay, let's try thetas in the neighborhood, right?
So that's what you mean. So if you only care about one value of theta, and you don't want the posterior distribution, then you use the optimizer.
Okay.
So but in Bayesian, we don't only want one value, we want to have a posterior.
So when you say that, what you're really saying is that you want to, in particular, only draw from this prior distribution and see how they interact. And that just feels like
I really want that.
So basically what you're saying is that the fact that you really want to incorporate your prior is sufficient to do like 100 times as much work, something like that.
Because
is that worthwhile?
It depends on the there is, and certainly on the data.
So
I have a genetic example, an example that I come from my practice. When I work with some
machine will have 5 samples. You only have 5 samples. So if you do the empirical mean, you will have one value. Imagine it's 0.2. But they don't really care about they have a second sample with another empirical mean. They want to know if these two empirical means are close or how. They want an uncertainty around this empirical mean. So either they do a frequency calculator, they do a confidence interval, etc. Or they compute the uncertainty in a probabilistic way. So this way I can tell you then that the empirical mean here, and maybe the distribution like that, I can tell them that this is all the likely value of your mean. I don't tell them the mean is that. I tell you all these values are likely, and 0 is maybe as likely as your empirical mean. And if you have data that you don't trust completely, so again, when the number of observations tends to infinity, then they all but in practice, it doesn't tend to infinity. In practice, you have to decide, do you prefer take into account the uncertainty rates, and that's really different from the frequency simulation. The frequency you say, I just believe in my data, and that's it, and even if my data set is small, the frequencies I say I include the prior effects. I don't want to say there is one bad and good. I do both in my work. Really, I do both. But in one case, I know that I will have uncertainty taken into account, and the other one I will not.
And it's worth doing under 100,000 times as much work to be able to incorporate a prior.
In many cases, yes. Especially if you want to give I don't want to give them a parameter. I want to tell them what they can do to improve stuff. And to do that, I need myself, because usually I don't give them parameters like approximate. I tell them stuff. So they might want to say, I want to do prediction. What other experiment I need to do? Then if I only have one parameter, I can do all the predictions by one parameter. If I have a sample from a posterior, I can do the prediction by all of them and have some uncertainty on my prediction and all that. And tell them if you do this experiment now, you will improve your results. I cannot do that if I don't know. So it really depends on what you want to do afterwards. It's not. It really depends on what you want to do. Oh yeah, if you have a machine that is conjugate. If you have a model that is conjugate to the prior, you can use it analytically. Not the case. Now, there is a very recent paper from students who does some bootstrap. Using some bootstrap ideas and prior specification. That is very efficient. That's very necessary. There are some ideas going on there. Some people are trying stuff. We'll start again soon. You can. No, we can just finish, but I just by the time everybody's.
My only sort of sense of all of this is that it's you're doing like a lot of basically guesswork, so much extra work to be able to incorporate these things. Is there really no smarter way to incorporate a prior than just guesswork?
No, we sample from this. That's fun, and then no. Yeah, we need to continue. Yeah. Okay, let's go.
Okay, let's continue. Shh. Oh yeah, that works well. Shh. I promised you some slide on ABC model selection. You don't want to miss that. So what is model selection? Have you seen some model selection during this week and a half? Yes? Oh, great. I don't have to introduce everything then. So model selection, imagine you have a data and you have some candidate models and you want to know which one best explain your data. Here's a very basic illustration, and of course, then there is a trade-off between complexity of the model and fit to the data. A more complex might overfit the data. I think you know that doing machine learning in summer school. So in Bayesian, how do we do a model selection? We compute the posterior of the model given the data, and this is the likelihood of the data given the model times the prior of the model. What is, well, here I haven't included any parameter, which is not really great because in practice you have parameter. So how do we compute this thing, which is the probability of the data given the model? We integrate out of all the possible value of the parameter. So we say that this is the likelihood. So now the likelihood will depend on the model because we have many models with different likelihood. So we have the likelihood of the data given the parameter and the models times the prior of the parameter given this model and integrating out the parameter. So in a way, if you want to do model selection in Bayesian, you have to compute a very big integral, which is not great in practice. So you don't do that, of course, except if you have some conjugate model or stuff like that. But here you integrate over all your parameter space, taking into account the prior. If you have a uniform prior on a 10-dimensional, well, forget about it and don't do this integral, please. So how do people do it in practice? They compute this ratio, which is the ratio of the evidence between the two models. So it still involves these two crazy terms. But that's to compare two models. And if this ratio is big, then one model is favored. If the ratio is small, the other model is favored. And Jeffrey gave us a scale to say what is big and what is small. If you want to Jeffrey scale, you just type Wikipedia and you have Jeffrey scale. So typically people, when they do model selection, they compute this base factor here, involving a crazy integral, and they use the Jeffrey scale to choose which model is best between two. Of course, we don't want to do this crazy integral. Yes?
Can you give an example of what the model would look like? Like, I'm confused with like what it also.
That could be three models. One is a quadratic, one is linear, one is.
So that's an assumption.
That's, three models, the data are here. Of course, you don't, that's going to be more complex than that, but that's a very simple example. Yes?
In the ABC case, that would correspond to 3 different simulators. Like,
Yeah, 3 different simulators. Yeah. And that could be a linear simulator, a quadratic simulator, and a very complex spline simulator or whatever. Okay, so how do we compute this thing that is crazy expensive to do? Well, if you have very nice prior, very nice likelihood, you might be able to compute that analytically. It's a very, very rare case in practice. So some people suggest to use important sampling approaches, a bit like what we discussed just before. Some people use sequential Monte-Carlo that allows you to compute the model evidence. So if you have the likelihoods, there is a literature on that. I'm not here to talk about all the literatures in when you have the likelihood. I think you've heard some yesterday. But there are methods that can deal with that. One of the main ideas is to perform informant in the joint space. So have the model, the index model, that can be 1 or 2, or more if you have more models, being just an extension of your parameter theta. So you have a parameter theta that is your parameter for a model, and then you add to it the model as an index, and then it's more or less as doing a normal parameter inference algorithm. Of course, it's not that simple, but that's the idea of some approaches. So how do we do it with ABC? But we do that in a very, very simple way. We assume that M is just another parameter, so that's the same algorithm than before, but I just include the model. So at each step, I will first sample a model from a prior over the model. So here you can incorporate some belief that you had in advance of which model is the best. If you don't, you just do 1/2 on your 2 models. You don't need to put some information here. So you generate a new model from your prior. Given the model, you sample from the prior distribution for your parameter. So here indexed by M, which says that it's a prior for this model M. You might have different prior for each model, of course, because you can have different type of parameters. Then once you've sampled a parameter, you generate the data. So you use your simulator associated to this model. So the model M has a simulator FM. Use this simulator to generate the data. And then you compare the summary statistics and you accept, reject. And what you will accept is not only the parameter, but also the model index. And you do that n times, well, not n times, until you have n accepted particle, which is usually much more than n times. And you have your sample, and then you can summarize the information on the model. Yes?
So you need a finite set of models in this case?
Yes. All what I'm going to discuss today assume a finite set of models. Yes?
Do I assume that all your models involve a same number of parameters?
No. They can all have a different prior, and the prior can be on different, the parameter can be on different dimension.
But then we have a problem with bias factor because our complex model will always, like almost always have higher bias.
So that's the Occam's factor issue. And in Bayesian, we can see that if you don't have a lot of data, the simplest model will always be better. And if you have more data, the complex model will be favored. So there is a trade-off.
How do you penalize for the number of parameters?
From the prior. So how do I give that an explanation that is easy? Since the way is you will sample from your prior. Imagine in one model has a small dimensional space, so 1 dimension. The other has 10 dimension, to go to extreme. It's going to be easy, well, not easy. Even if just a few parameters on the simplest model explain the model, you are more likely to sample them by chance than in a very high dimensional space. You see what I mean? Because you will sample from a prior. Imagine it's a uniform prior, just to simplify everything. The complexity comes from this domain, and if it's big, the chance that you will pick a parameter in this 10-dimensional space that will exactly fit your model, but fit your data with the model, is smaller than the chance that you will pick a parameter in one-dimensional space. That's the idea of the Occam's factor. We can talk about the Occam's factor after because it is a very complex, and I've had debates with colleagues for hours on it. So if you have one thing to remember is that Occam's factor is the idea that if you don't have a lot of data, the simplest model will be favored. And more data you accumulate, more the best model will be favored. So when you don't have a lot of data, the simplest model will be favored even if it's not the best model.
Will Bayesian information criteria work for the model selection here?
Sorry, Will?
Bayesian information criteria?
Yes.
Okay.
You could use BIC, of course. But BIC will, no, sorry. BIC will work if you have the likelihood.
Okay. Thank you.
BIC involves the likelihood, huh? So, in the previous slide where I made a list of algorithms that work when you have the likelihood, I should have listed BIC, but we don't have the likelihood. So that's just an illustration. That's exactly a summary of the model on the algorithm. Imagine we have 4 models. The idea is just we are going to sample one randomly among the 4. We are now in the space of this new model. We are going to sample a particle from this, a parameter from the prior for this model, simulate data, compare to our real data, and accept or reject. Here we reject, and we say, oh, we have a 0. Then we sample a new model. It could have been the same. Now it's M3. We simulate data. Well, we simulate a parameter, and we simulate the model to use to generate data. Here, for simplification, because I had this graph, the parameters both live in R2, but they could live in different dimension. And here, the data are close to the simulated data. The observed data are close to the simulated data. So I will accept this parameter, and I will say, oh, I accept this model too. So I will put a 1 in front of M3. And I do that many times. And at the end, I will obtain a vector of how many times did I accept a particle in each model. And that will tell me I favor model 1 here. And then model 4 is maybe good or 2. Model 2 and model 3 are not great. So that's the way we infer which model best explains the data. It's very simple. Huh? Yes?
In this case, you also get the posterior, like you get the posterior samples of all the data.
You have both of them. You have the joint between the model and the parameter. So you can look at the marginal of the model. You can look at the marginal of the parameter for each model. You have the joint.
Is it worth it, like, to take the model that you pick and then
if you want a more precise, yes, it might be worse. It kind of depends on which ABC algorithm you use. So the posterior probability of the model is just a frequency. So you sum up how many times did you accept this model, and you divide by the number of times you accepted something. That's very easy. As with parameter inference, there are variants of it using MCMC, SMC, and different algorithms, mainly MCMC and SMC. I'm not going to give you them. You had MCMC and sequential ABC, that's fine. But they can be adapted for model selection exactly in the same way. And there are papers associated to all of them. There are also ways to do the posterior regression that we mentioned yesterday. So post-processing, re-rating your particles, that's also feasible for model selection. So all the things that I talked about yesterday and today for parameter inference can be adapted for model selection. I would say all except the summary statistics. And that's where we are going to have to talk about it a bit, because that's a very tricky thing. So everything that I've talked about can be adapted to model selection except the summary statistic. So there are some questions that are still more or less open questions in the field. Should we have the same epsilon for every model? Not clear. Should use summary statistic vary across model? I will talk about that. People are clear about what we should not do, and some people have suggestions about what we should do, but now it's clear what is a problem. Should the distance measure vary as well? That's also not completely clear. So there are some points that are not completely clear. It's working, we have some proof of convergence, but still, if you want to improve stuff, there are some areas of improvement. So let's talk about the problem of summary statistics. But just before, I just need to summarize what is the base factor that we obtain. So the base factor in general is the one on the top. That's the same one as I mentioned at the beginning of these slides. And that's what we are aiming towards. And the base factor that we obtain using the ABC is the one at the bottom. So we have the prior of the model. And again, that could be just a uniform prior, so it could cancel out. And then we have just an indicatrix of number of times we accepted the model and times like we accepted the distance. So that's the base factor we obtain. There are many ways of writing this base factor. So here is the base factor if we fit T, the number of simulations necessary for N acceptance. Because there are just different ways of writing the base factor. Okay? Robert and al. Is a very good reference for problems with model selection using summary statistics. If you want to read more about it, they have a great paper on it. I will show you some slides from them, but they have much more things. So I have many gray area in the next two slides. The gray area are repeat from the previous slide, just for you to have the notation still there. Yes?
Why do we need to multiply by the number of cases we chose the model if we have that already in the prior and actually the factor is given and more?
Sorry, that is not. Why is it related to prior? Yeah. Yes, so that's the same as the gray part. That's why I didn't move.
Yeah. So on top it's pi of x star given m1, and then that's in the
this one, or this one?
So on the left-hand side, yeah, that's in the equation down there.
So you're looking at the equation down?
I'm comparing that one with the
Okay.
one, and I'm confused because here you have you count the number of times you choose model 1, right? That's like the indicator function of MT.
So let's look just at the bottom one then. There are different ways of writing the bottom one. Here is assuming that we T is the number of simulation. So it's not the number of time we accepted, it's the total number of simulation we've done. And we've accepted only N of them. So we do the sum, for some T, it will be a 0 because we will not have accepted anything. Is it clear? Because there are different ways of writing it. I could have written it just making the sum over the accepted one only. And then I will not have the second term. I didn't want to write all the options here, but yeah. Okay? So just because people were wondering, okay, we have this base factor, that's the one we are estimating using model selection and ABC. What does it converge to, by the way? Do we have some guarantee that it converges to what we want? So that's what the people looked at. So basically, to converge to, there are two things. We want first the epsilon and then eta. So here first say, okay, if epsilon tends to infinity, the term on the top can be replaced by the integral over the different z and theta 1, and one for the theta 2. So that's just Monte-Carlo integration, Monte-Carlo convergence. So that's fine. So when it goes to infinity, we obtain this term. And we just, for the first line to the second line, we do a change of variable to highlight the dependence on eta. So we see that if we change the variable, we replace z by eta. Here we have the distance between eta z and eta h star. So here we'll have the distance between eta and eta h star. And here, instead of having the likelihood z given theta 1, we'll have the likelihood that depends on eta. So it's just a change of variable. Huh? It will just be convenient for the rest. So no magic here. So we'll do this change of variable. I remember just eta is a deterministic function of your data. So you can, if you have the likelihood for z, you can have the likelihood for eta z. It's a deterministic function. Again, the gray area is exactly the same as the previous slide. It's just for you to have it all in the same slide. So when epsilon goes to 0, this thing will converge to, so the distance will go to 0, so it will cancel out, and we'll just have this quantity appearing. And that depends on the distribution of eta under each model. It's not that surprising, huh? All ABC is based on comparing eta on the observation and eta on the simulated data. So it's not surprising that the base factor depends on eta. It's not surprising, but it's not what we wanted. Because the base factor we had in mind, the thing that we aimed, was this thing, but not with eta here, but with the likelihood. So in a way, our ABC scheme converges to something. It does, that's good. Already, we are reassured. But it doesn't converge to the thing we want it to. It converges to something that depends on eta, and that is not the base factor we wanted to, which was this thing for the observation directly and not the summary of the observation. That's where people started worried. So if eta is a summary statistics, a sufficient summary statistics, sorry, eta is a summary statistic. If eta is a sufficient summary statistics, what does that mean? So sufficient summary statistics means that the posterior can be completely recovered if you use eta or if we don't use eta. Huh? So if eta is a sufficient summary statistics, using eta or not eta gives you the same result for the posterior. So people usually use in ABC when they can a sufficient summary statistic because they are happy with it. We have all this guarantee, that's great. Robert and Hal pointed out in this paper that even if we use a summary statistics, we don't have the correct base factor at the end. And that's blow away many people. Because that's what most of the people were doing. They were thinking they were converging to the right thing and they were not. So that's just a proof of what's happening. Is just a change of variable again, but a summary statistics by definition is, for each summary, if there is a summary statistic, we can rewrite the likelihood as the likelihood for the eta times a function. That's just a definition of summary statistics. So if eta is a sufficient summary statistics, then there exists a G such that the likelihood for the data and the likelihood for the summary statistics are just linked by using this G function like that. And so on the top, this thing, this is the base factor we want to obtain. And so if you rewrite things with the G, that's the base factor you want to obtain. And here is the base factor we obtained in the previous slide. So that's this thing times this thing without the G. And that's this thing times this thing. So basically, the base factor we obtain when epsilon goes to 0 using the ABC model selection algorithm is that term. And the base factor we wanted is the one there. So except if G is identity, which means that eta is identity, even if a statistic is sufficient for your model, sufficient for parameter inference, it will not be sufficient for model selection. Maybe you don't care. I mean, that in a nice way. Maybe you're like, okay, but we do model selection based on our summary statistic. Our summary statistics are good enough. We believe this summary statistic, and that's fine. In which case, that's great. And that's what I do in practice, because we need to do something. But you need to be aware that it's not the same, and if you use a different summary statistic, even a different sufficient summary statistic, you will obtain a different base factor and maybe make a different choice on your model. And I think it's worth just knowing. So basically, what I just said is that if this ratio is equal to 1, they are equivalent, but it's very rare that this ratio is equal to 1. And then a lot of people worked on how can we do then. So how can we do? Some people try to indicate when this ratio is equal to 1. It happened in some cases, that's good. It's not all the cases. So if some models are nested themselves in a submodel, which is some cases, then the ratio is equal to 1 and everything is fine. There is also a recent paper by Mara and al., which is a lot of proof. So if you want a lot of proof, you can read this paper. It's a great paper, but it's really a lot of proof. That proves some necessary condition for the ABC model choice algorithm to converge to the true model. I will not give you all the proofs. But the necessary condition is that when the sample size increases, the posterior mean of the prediction of the summary statistics converge to different values. And that makes sense in a way. We base all the information on the summary statistics. So what we want is that more sample we have, more data we have, we want these summary statistics to give us information to separate the two models. If they give us no information to separate this model, then we will not be able to separate this model. That's just as simple as that. So I have an example in the next slide. I think I have many examples now. It's a lot of slides with figures. Here is a very basic example, and of course we don't need ABC for that. It's just to illustrate the point. So we assume that we have two distributions, a normal distribution and a Laplace distribution, and we want to estimate their mean. They have the same variance. We want to estimate the mean, and we put a normal prior. And we use different summary statistics. So the sample mean, the sample median, the sample variance, the median absolute deviation, and the sample force moment. The blue one are sufficient statistics for parameter estimation to estimate the mean for each model separately. So the sample mean and the sample median are sufficient statistics if you want to do parameter inference of normal or of Laplace. The green, the sample variance and the median absolute deviation are ancillary statistics. Do you know what is an ancillary statistics? Anybody knows? Yes?
Let me try to recall the statistics. An ancillary statistics is something that if you condition in it, the statistics goes away or something?
Yeah, so in a way here, it's a statistic that does not depend on your parameter of interest.
Like a pivotal quantity.
So here, the sample variance doesn't depend on the mean. We know that. The mean absolute deviation doesn't depend on the mean, and the parameter of interest is the mean. And the last one is one that will work for model selection. And I will show you that it's working in the next slide. So here is the posterior distribution using ABC, just ABC, with an epsilon 1% distance quantile. When we use both the sample mean, the median, and the variance together as a summary statistics. We can just see that if the data are generated under Gaussian or Laplace, in both cases, we don't manage to separate the model. So what x-axis is just which model has been used to generate the data. So either a normal distribution or a Laplace distribution. And the y-axis is the posterior probability of the model. And in every case, the posterior probability is around 0.5. ABC does not manage to tell you if it's a Laplace or a normal, even if you have more and more data. And here is the number of data you have. So even if you have 1,000 data, if you use these summary statistics, ABC will not tell you what is the difference between these two models. Just impossible. But if you use the force moment, you do. So if you use the force moment, more data you accumulate. If you have more data, then if you sample the data from a Gaussian distribution, then quite quickly you will have a posterior picked on one saying, yes, it is definitely a normal, it's definitely not a Laplace. It's a bit more tricky to explain why it's not that clear for Laplace. In Mara and they explain the result, and the result is a very particular case on this specific simulation scenario where theta is 0. So that's an odd thing happening here. But in general, if you use the force moment sample here for this case, then you can separate out pretty clearly what's happening. And why is that? I've written here the sample, the force moment for the normal and the Laplace. And what Mara and Al said is that the summary statistics needs to converge to two different places. Here theta is 0 for this, the data has been generated with theta is 0. So for the normal distribution, the force statistic, the mean of the force statistic, will go to 3 for the normal, and will go to 6 for the Laplace. So they go to different values, and that's enough. So Mara and Al just said the best, the summary statistic that will work to discriminate between two models is a statistic such that the posterior mean of the summary statistic will be different between the two models when we have more data. Any question on that?
What's on the y-axis, sorry?
The y-axis is the posterior of the model. And 0 means Laplace and 1 means normal. You know, it's a posterior, so we have to choose which one is. Yes?
So in this case, it looks like these two curves in theta don't intersect, so maybe it didn't matter as much which point theta you chose to generate the models from. But are there cases in which the choice of theta you get?
Yeah, so there are some observations for which two models are much similar than others. But in fact, again, this is simple model where we generate, where we have the likelihood. In general, you have the observation. So here I simulate data from the model to obtain observation. In general, you have observation, and you want to do inference for that observation. If the two models don't discriminate for that observation, that's fine. You can just say the two models explain as well my, that's a result. Huh? And in which case, that's good. You choose the one that you prefer, the one that is computationally less expensive. It's not a big deal if you don't manage to discriminate. You don't always want to. If you have a finite set of data, you might just want to, like.
And in advance, when you were choosing these summary statistics, you would try to look for ones that have this property.
Yeah.
So this is something you could run in advance if you thought about it without just trying things out.
Yeah. That's exactly what they suggest here. So I cannot do a review on summary statistics. There are many papers appearing, and there are, I wouldn't say every day, but every second month there are new ones, so there are many. Basically, based on this idea from Marin, but already before some people proposed things, and then there are more and more people proposing approaches to identify good summary statistics for model selection in advance, like. There are some based on, so there is the one proposed by Marin. All of them are based on trying some preliminary data, but there are many ones. The most recent one is based on random forest. It's a very interesting one. I wanted to present it here, and I thought, no, I don't have time. So you can read it if you want. That's a really interesting one.
Can you just say what the inputs and outputs of that are?
Now we'll talk about it offline. Yes? You had a question?
Yeah, sorry. So in this example, the only thing that was different between the two models was the noise distribution, but I'm wondering how such methods extend to cases where your models include a different number of parameters. So is it necessary that the summary statistics lie in the same dimension space for each of the models?
I don't think so, though some of these methods might depend. So I haven't done I should reread the paper, re-rank and think which one apply only, people develop method and some say, oh, this only work in this condition or this work in all conditions. So maybe not all the approaches work in every condition. So usually it should, but in practice when you find a solution, it might not work on every condition. Yes? So I just wanted to finish with an example. And that's a real data example where there is definitely no likelihood. That's an example coming from some collaborators so yeah, my thing is not going to replay automatically, so I'll have to click. That's not. What do you see here is a zebrafish. So it's a small fish, and there has been a wound here. Tail has been cut. And what do we track are some cells in the fish. They are leukocytes. They are cells that should go into the wound to repair stuff around. So in all our body, we have leukocytes, and they move around. And I'm doing a simplistic biological course, really simplistic. They move around, and if there is a wound happening, they will go to the wound and try to do something in order to repair or call some friends who can repair. Basic biology, huh? What did they do here? They track the leukocyte cells. So we have 6 or 7 leukocyte cells, I don't know, well, whatever, 8, I don't. All these dots, blue, are the leukocyte cells, and they are moving. And some of them are moving towards the wound. They detected there is a wound that they are going towards it. The wound is here. And some are not at all, and they are moving around. And the collaborators here, so I'm a collaborator of Felipe, but I haven't worked on that project. I thought it's a cool one to show. They were trying to model how the leukocytes react when there is a wound. So what happened in reality is that here there is a stimulus, so there is some cytokines that is released. So as soon as the wound happens, there are some cytokines that are released, and the leukocytes should detect the cytokine and say, oh my God, something is happening, let's go to the wound. That's what's happening in the biology. What they observed is the movement of the leukocyte. So they first had to do a cell tracker that we show here. So that's the first part of the work that's done. And then they had different models to describe how the leukocyte might move. First, like, is it a random walk? So it's a random walk, but it's a random walk that is biased towards the gradient of the cytokine when they see it. So usually, as soon as they detect that there is something, so they detect some cytokine, they need to go towards a higher gradient. So there is a wound, there is some cytokines that are released, and the leukocyte that moves say, oh, I feel like leukocyte, a cytokine, should I go there or there? And it tries to go to the higher gradient to go towards the wound. So they have 3 models. So now the wound is in the opposite, because of course they had a lot of them. So they have 3 models. Each of them takes into account different cytokine gradients. So again, that's the wound, there is cytokine being diffused, and that's the distance to the wound. And then they had 3 models of how the concentration of the cytokine decreased towards the distance. So is it a linear decrease? Is it, they have different models. And that's exactly what they've done. They've done ABC-SMC for model selection. So I don't have the result because in a way there is no result to show because the data, in all the toy example I can show you fits to the data. What is a fit to the data? It's a fit to trajectories here. It's impossible to show. But what they've done is that they had a lot of these movies, the one that I've showed you before, they had a lot of them. They summarized that, they used many summary statistics. Hopefully some of them were sufficient for model selection. They had these 3 models. They used ABC-SMC, encoded in the ABC-SysBio package, because ABC-SMC for this complex data, you don't want to encode it by yourself, and you want to have someone who coded it up. And they identified that the model 3, yeah, I think it's model 3, is much higher, so there is much more evidence based on your data for model 3 than all the other models. And then they published a biological paper on that, and that there is all the biology related to it. Yes?
So how did they choose the prior over models? Or how do you generally use
So over the models, it's uniform prior. On the parameters, I don't remember. We need to check the paper. But no, what I can tell you, because I know how we do it together usually, we try to use uninformative priors based on a range of plausible biological values. So that we know the parameter can be biologically between that and that, because we know that the leukocyte cannot do more than this, something like that. And then, but we know that we have an upper bound, lower bound, and then we do either uniform or broad uninformative. That's what we typically do. I need to check what they've done here, but I'm pretty sure knowing the code that you've done that use that.
But I thought you want to penalize complex models, right? So how would you do that?
As I said, complex models are automatically penalized using a Bayesian framework if you have not enough data. That's the Occam's factor. We can have a group discussion on Occam's factor after. Any other question? So that's just to illustrate to you how we do it in practice, really. That's my take-home message for this all ABC class. So main thing you have to remember is that ABC is used for parameter inference and model selection when we cannot compute the likelihood. So we have a model, we can simulate from it, but we cannot compute the likelihood. The simple approach is obvious to do. You can implement it, you will implement it today. It's very easy to do. Be careful, the choice of summary statistics might have a huge impact. You're warned now, cannot say in a few years that you didn't know. You know. If you want a computationally efficient approach, there are many. I talked about ABC-MCMC and the sequential ABC with an optimal choice of perturbation kernel. There are others, but that's the two most famous ones. I wanted to have a slide on computational resources to do ABC. And then I went to the Wikipedia page of ABC, and they have a great table with all the computational resources I know, even some I didn't know, with a summary of what is the assumption of each, what's the language. So I thought I will tell you to check that out. So there are some in R, there are some in Python. I've helped a lot on the ABC-SysBio, which is ABC-SMC implementation in Python, really tailored for system biologists in the way that you can implement your model even not knowing how to code Python, which is very useful for bioinformatician. We can just explain the model in an SBML file, and then we transform it in Python, and it runs on CUDA. That's what we've done a couple of years ago. But there are many others, and there are more and more every year. So when I checked the Wikipedia page, I was really surprised that there were even more nowadays. Here are some references. It's for you. We don't need to go through them together, but there are some on the basics, some on review articles that I've used, some on theoretical results, post-processing, and application. MCMC and sequential approaches. I tried to be non-exhaustive, but there are still a lot. And some summary statistics algorithm. That's it for me. We are going to talk together again in half an hour for the tutorial. Thank you very much.
I don't know.